We finished our specific discussion of gases, and in this portion we're going to talk about intermolecular forces and what makes substances, solids, liquids, or gases based on the forces that hold them together. So intermolecular forces are attractive forces that exist between molecules. All right, so this isn't within the molecule. This is what's holding the molecules together, whether they're a liquid or a solid or a gas. And in order of increasing strength, they are London dispersion forces, dipole-dipole, and hydrogen bonding. And the strength of the intermolecular forces is going to determine if a compound has a high or low melting point or a high or low boiling point. And also it's going to dictate whether or not it's a solid, liquid, or gas at a given temperature. London dispersion forces are weak interactions, and they're due to changes in electron density in a molecule, and this is often referred to as a temporary dipole. And what basically happens is, as these things are zooming by each other, they have electrons around the nucleus. So let's draw a little nucleus, if it'll let me. Little nucleus, and then you got electrons, right? So I'm going to do minuses for electrons. And usually those are going to be evenly distributed between these atoms. What happens is, if it comes by a covalent or a molecular compound that's like got a dipole, so that is, it has more negatives on one end than it does on the positive, in this case electrons, and so it makes this end positive and this end negative. And so when it comes zooming by this other molecule, if the negative side is oriented towards this, what it's going to do is it's going to make those electrons try to get away from there. And so all the electrons are going to try to move over here, and that causes a temporary polar situation where you'll have negative and positive on this end. And as soon as this polar molecule goes by, it goes right back to the way it was. So that's what we call a temporary dipole. A permanent dipole, I'll show you in just a minute, is one that it just inherently in a molecule causes it to have more electrons at one end or the other. So this weak interaction between the temporary dipoles is what causes London dispersion forces. And these are going to be the temporary attraction right here between these two molecules. All covalent compounds exhibit dispersion forces. The larger the molecule, the larger the attractive force, and the stronger its intermolecular forces are. So if we just look at this, so we've got methane. Okay, methane is not typically a polar molecule. Okay, it's just kind of everything is sort of distributed. So we think of it as nonpolar, and it's got a C, and when we write it just flat screen, you can see why it would not be polar, because everything is nice and symmetrical around that carbon. Sorry. But London forces can be still between these, because there is some, even if it's super tiny, region in this molecule where the density is of electrons is going to be more on one end than the other. And so when you have more negative on one end, that produces a somewhat positive end, and so the negatives and positives are going to be attracted to each other. Again, you can see why this is a super low type of attraction. It's the weakest type of attraction that there is. Now, a dipole-dipole interaction are between two polar molecules, and polar molecules have a dipole all the time. And so in the case of formaldehyde, you can see you've got hydrogens on one end and you've got this big O oxygen on the other end, which has a lot more electrons, and so it tends to pull most of the charge towards it, giving it a slightly negative end. Well, if it's going to be attracted to another formaldehyde molecule, it will be attracted to that slightly positive end of the next one. And so there's this sort of attraction and attraction. And then what that does is it ends up holding those molecules closely together. And that's why formaldehyde is a liquid. Hydrogen bonding occurs only if, number one, you have a hydrogen. There's a clue. And also, if you have oxygen, nitrogen, or fluorine. Those are very electronegative ions or atoms, and they are going to attract hydrogens. And so when the hydrogen of one molecule is attracted to an electronegative atom such as oxygen, nitrogen, or fluorine, it's going to have an attraction. These hydrogen bonds are the strongest of these three types of intermolecular forces, and they will hang on pretty tight, but luckily we have lots of enzymes that can break those bonds depending on what they are. Hydrogen bonding plays a huge role in DNA and RNA, especially in DNA, because in DNA the helix is going to be shaped based on hydrogen bonding between each one of these strands. So you got one strand going that way and one going this way, and they are attracted to each other. And so if we zoom in on that a little bit, you have an oxygen from one bonding to a hydrogen of another, hydrogen to nitrogen, hydrogen to oxygen. All right, and so these dashes are hydrogen bonds, and so in some molecules they can form 3, and others they can only hold 2, and that's why you can only bond certain amino acids to the others. Not also true, but nucleic acids, I should say. All right, so just to summarize, London forces are the weakest. They are exhibited by all molecules, and examples are methane, H2CO, and water. Dipole, moderately strong. It's molecules that have a net dipole. That is, just because of their structure, they have a dipole, so they're polar. H2CO also, and water can form dipole-dipole. Hydrogen bonding of those, though, is going to typically be between an OH, an NH, or an HF bond, and so water is a perfect example of a hydrogen bonded material. I mentioned at the beginning that this intermolecular attraction can affect boiling point and freezing point. So we're not going to do calculations with this, although if you're curious, I think we have some in the book. The boiling point is the temperature at which liquid is converted to a gas. All right, the melting point is the temperature at which a solid is converted to a liquid. The stronger those forces are, the higher the boiling point. Think about it. In order to get it to change phases, you're going to have to separate those materials from each other. And so as you increase the strength, it's going to be harder to separate them. Therefore, you're going to have to heat it up higher, or to boil it, or heat it up higher to melt it, either one. So an example, if we look at methane, as we were talking about earlier, methane, which is CH4, and water. Okay, methane is not polar, and so it only has London forces. And its boiling point is a negative 162, and melting point is a negative 183. That's really low, guys, in case you haven't thought about it. Water, though, is hydrogen bonded, and these are stronger forces, And so you have to heat it all the way up to 100 degrees to get it to boil, and you have to get it up to 0 as opposed to minus 183 in order to melt ice. Okay, so since we have the dipole here, which is a hydrogen bond, and a type of that is hydrogen bonding, and remember it's going to the other molecules. Which is holding it together really tight, so you have to heat it way up in order to separate these molecules and let them get farther apart and become a gas. With propane and butane, typically the larger the molecule, the stronger the forces are going to be. And so if it's got a higher molecular weight, or formula weight, then it's going to have stronger interactions. If it just looks bigger, it probably is going to have stronger interactions as well, as you can see in that example.